Up until this point, we've always assumed that our populations are in a contiguous bit of habitat. That is, then they can easily move around within that bit of habitat and interact with each other, mating and feeding and things like that. But in the real world, one of the biggest problems we have, especially for threatened and endangered species, is habitat fragmentation. Habitats are no longer contiguous. They've been broken up by roads, development, agriculture, many kinds of anthropogenic disturbances break pieces of good habitat into smaller pieces. One of the first theoretical approaches to try and understand what the effects of this was what is now called the Levins metapopulation model, after Richard Levins, the guy who first proposed it. In a Levins metapopulation model, we basically think about subpopulations, which are either occupied, if they're solid colors, or unoccupied by a given species. In the simple model, they're all the same size, they're all the same distance apart from each other, there's no heterogeneity. There's just some proportion of our patches of population of habitat are unoccupied and some are occupied. The main processes in a Levins metapopulation model are colonization, where an occupied patch contributes members of the species to an unoccupied patch, and so this unoccupied patch is going to transition to become occupied at the next point in time. And extinction, where a currently occupied patch, that subpopulation disappears. So at the next time step, we've got no individuals here, they're now unoccupied, and this patch up here is now occupied. So we basically have a rate of colonization and a rate of extinction in our metapopulation. So rather than talking about births and deaths of individuals, we're talking about births and deaths of occupied patches. The equation for this model comes out looking like this. So there's a term that describes the rate at which patches are colonized. So little c is the colonization rate, p is the proportion of occupied patches. So this whole term gives you what the rate of colonization is, and then we have p patches occupied, and so those patches go extinct at some rate e, and so there's a minus sign in front of that. So we're adding the patches that are being colonized and subtracting the ones that are not being colonized. If you rearrange this a little bit, it actually comes out looking a lot like the logistic equation. And when you plot out this expression, so now we have p going from 0 up to 1, and we're now plotting out dp by dt for particular values of c and e, c at 0.1 and e at 0.05, we get a quadratic curve much the same as we get for the logistic population. And so the equilibrium points, that is where the rate of change in p is 0, occur wherever dp by dt is 0, so wherever this line is crossed. So when p is 0, our rate of change is also 0, because this whole thing, everything's 0. But that's an unstable equilibrium, because if it gets just a bit bigger than that, then the rate of change is positive, and it's going to increase until it gets to this point up here, where it's also 0 again. But if the metapopulation deviates below this point, then the rate of change is positive, and it's going to get driven back towards this equilibrium point. Conversely, if it gets above, there's a higher proportion than in the equilibrium, then the rate of change is negative, and the population is going to get forced back here. So this is a stable equilibrium point, just like the carrying capacity in a logistic population model. There's a very simple expression for where that equilibrium point occurs. It's just going to be 1 minus the extinction rate divided by the colonization rate. So in the previous graph, the colonization rate was 0.1, this is 0.05, so that ratio is half, 1 over 2, so P star is at 0.5, and that's where this equilibrium point appears on this graph. The only time, one of the most important insights from this model, which is admittedly much oversimplified, but one of the most important insights from this model is that as long as there's some probability of extinction, that is, it's not zero, then there will be some patches of suitable habitat, that it places these species could exist, that will be unoccupied. And as we saw in the previous graph, if the extinction rate is a sizable fraction of the colonization rate, then it could be a large portion of the habitat, available habitat, is unoccupied. If the extinction rate is bigger than the colonization rate, then there is no stable equilibrium point. Then at that point, the system is going to go to P equals 0. So as with many of these systems, we sort of really are operating in the hopes that the ratio of these things is less than 1.